meeting and choosing such a perfect time for it. Okay, so I'm going to talk about the dissipative system. What I want to do is to just mention two very well-known open problems for this general system. These two problems are very difficult, and therefore it's good to bring up from time to time. Very difficult and very important. Okay. So there are three systems that I mentioned here. The first one is Hyperbolic Conservation Law, which usually people call the Inviscid Dissipation. And that dissipation, the source of that comes from nonlinearity and something called Entropy Condition. Then there's a Viscous Conservation Law, which clearly has a dissipation because you have a higher order term there. So there's this derivative term, which is a second derivative like heat equation. So that's a dissipation. But it's important to know that the dissipation really is a combined effect of these two terms. Because nonlinearity, as I said, in the first equation, everything has a dissipation. And this is the difficult part of this, to realize that, and which is not exactly completely understood. Then there's the Boltzmann equation, which everybody knows. There's an edge theorem, and which induces dissipation. But the edge theorem also has a very difficult thing, because edge theorem says that you multiply this by log f integrates less than or equal to 0. This is only one part of edge theorem. There's also this flux part and how this will interplay. And this is easily to be ignored, and that is not good. All right. So I'm going to first talk about the Hyperbolic Conservation Law. I'm going to assume it's a hyperbolic, means that there's a wave which propagates with the speed lambda 1, lambda 2, lambda 3. And there's a nonlinearity which says that this speed itself changes with the unknown function u itself. And that creates a shock wave, and which requires something called entropy condition. Together, it gives dissipation. So the most important problem to look at a conservation law is an initial data which consists of only two constant states, UL here and UR here. And that problem was first started by Riemann. Of course, Riemann has made a great contribution to geometry, but he also made important contribution to hyperbolic partial differential equations. So in this case, Riemann recognized that because the initial data here, just two constant states, the PDE itself has no low order term. So therefore, the solution itself of this Riemann problem is has this simple hyperbolic scale, uxt equal to u7x7t. So therefore, it's a function of x over t. And so basically, the PDE, which is a function of two variables, become the solution become function of one variable, and this become a algebraic or ordinary differential equation. And Riemann solved this for this particular case of isentropic gas dynamic. So it is a solution which looks like that. It's function x over t. Now this solution is important for the following reason. Because it is a wave which go into different direction. They don't do that. They do like that. Okay, the wave go like that. So it is a wave that scatters our way. And it represents scattering wave pattern for the general solution. And therefore, this is this theorem. This theorem says that if you want to understand this general solution of the hyperbolic conservation law, really, you need to only understand the structural Riemann problem, because the solution locally in time, globally in time, behave like a solution Riemann problem. And the proof is done using Gleim scheme, which is approximate solution by the Riemann wave pattern, and realizing that the only wave which is non-interacting are the Riemann wave pattern. And this fact can be quantified to be stable. Okay, this is a result of many people, but let me just say that, and you can easily believe. Oh, by the way, why solution become non-interacting, the scattered wave pattern? Because the solution do interact, but after interaction it become non-interacting, and for a very large time it can become non-interacting. For a short period of time, locally, in the forward time direction, it's non-interacting, okay, and therefore the theorem. This work, the most important work is the work by Gleim. He introduced this Gleim scheme, which is actually preceded by the work of Gortonov in Russia. Gortonov recognized that to approximate the solution to form a numerical scheme, it's a good idea to use the Riemann solution, because Riemann solution encoded in there the nonlinearity and entropy condition. Okay. Then Gleim and Lux has initiated the study of the solution regularity and so on, and I worked for a few years on this. Now about the viscous conservation law. That's the equation there. But I have looked at the artificial viscosity. So previously, in place of epsilon, I should have a B U epsilon then inside the derivative. So for this problem, there's a remarkable theorem which says that if you let this epsilon to go to 0, which is the strength of viscosity, to go to 0, then the solution will go to the solution of the hyperbolic conservation law. Now, this is a difficult theorem when you realize that the hyperbolic conservation law the solution has a shock wave, it's not continuous. So therefore, this process is very singular. You cannot just say that as epsilon go to 0, just go to 0, because the U epsilon sub Sx will go to infinity at the shock wave. Okay, so this number actually does not go to 0. It goes to 0 only almost everywhere. And at the where it does not go to 0, it's a shock wave and encoded the entropy condition. So the proof of this theorem is to generalize the Riemann solver that's used by Gleim. Gleim approximate solution by Riemann solutions, or in other words, he measured the strength of the wave by the Riemann elementary wave. Now, elementary wave for the hyperbolic conservation law is given by the Riemann problem. But elementary wave for the viscous conservation law is not given by the Riemann solution of the hyperbolic conservation law, of course. And instead is given by viscous wave, and that is captured by the center manifold theory for the viscous conservation law. And therefore, the proof is to use, instead of the inviscid Riemann problem, by using the center manifold coordinate, which is obtained for this equation. So in other words, this is a very nice excellent generalization of the idea of gleam. And it was done by Bianchini and Bresson. Okay. And Bianchini was in Taipei with me for half a year. When he did this, a surprising thing is that this result could not be generalized for the physical viscosity, such as Navier-Stokes equation. So how about the physical viscosity? Why physical viscosity is harder? And there are two reasons. One reason is that this physical viscosity, B, it is not positive. It's greater than equal 0. In fact, for many physical systems, it is 0, 0 on the first conservation of mass, and then something else here. Also, it is not diagonal. For artificial viscosity would be diagonal, 1, 1, 1, 0. And this has non-zero elements everywhere, and there's zero somewhere. And therefore, the coupling of wave of different family is stronger. And that makes the problem so difficult that it's still open. The open problem is show that the solution of this equation go to the hyperbolic conservation law as epsilon go to 0. And this problem is open. So in particular, for example, you want to show the solution of Navier-Stokes equation in gas dynamics will go to solution of all the equation as a heat conductivity and viscosity go to 0. Okay, that is an open problem. Yeah. All right, so let me introduce you a little bit this theory. This theory has been studied by many people, existing and so on. It started with the Russian, US, but I think the most clean and the nice result, a general result is by the Kyoto school. So there is something done by Kawashima Shizuta, which says that, well, this equation is not parabolic because the B is not positive, definite. But all the physical system has some property that, although it is not parabolic uniformly, but this is dissipative nevertheless. Okay. In particular, if initial data is not too rough, then the smooth solution will exist for all time. And these are the conditions. The condition that it should come from physics exists certain entropy pair, which was shown by Goldenov, Lars Friedrich, and others, saying that if you have entropy pair, then the system is symmetrizable. So this needs to be assumed. Another assumption is that, well, although B, it is not positive definite, but it should be positive definite where it counts. Okay, and which means that the eigenvector of the flux F prime should not be in the null space of B. Okay, otherwise it becomes some part of it is hyperbolic. Then you get a shock wave and so on. And then there's certain block structure, which I will not go into. So according to this theory of Kawashima Shizuta, then a smooth small initial data for the equation will give you global smooth solution if you assume all these three conditions. And this condition is good because it includes the Navier-Stokes magnetohydrodynamic and so on, and nonlinear elasticity. So it is a good condition. Now, I have mentioned that the understanding of the equation is very preliminary because, say, for example, in the Kawashima-Shizuda theory, you say that if initial data is small, smooth, then that's a global solution. But small and smooth solution would mean that this term, the dissipation term, has dominant effect. And hyperbolic term has a secondary effect. Okay. Now, as we know, it should be the combined effect of this. In particular, when epsilon is very small, then what happens? And that is a hard problem, and we have very little understanding. So I have proposed that we study the linear problem a little bit in more some detail. And the linear problem, of course, the simple linear problem is a linear equation around a constant state. In that case, the nonlinearity of the flux function is gone because linearize it. Nevertheless, the hyperbolicity and dissipation, the coupling of them is still left. And so this is a problem when studying. And the Green function for such a system has this structure. Don't look at it too carefully. Okay, I mean, this is not good. But this is RK, which means that the hyperbolic part dictates the propagation of wave, the direction of propagation of wave. Okay. And the parabolic part, of course, has some say. So this HK is the heat kernel. Okay. The heat kernel in the direction of lambda k. I must have written somewhere here. Ooh. Okay. I did not. Oh, here's the heat kernel. This one. Okay. So this is heat kernel. And the mu k is the diagonal element of the viscosity matrix when the hyperbolic part is diagonalized. Okay. So this is a primary wave, as expected. But there's a secondary wave, the subscale thing, which I call it script E1 and E2, which decay a little bit faster than the heat kernel because I have T to the -1/2. And the derivative of heat kernel always give you an extra T to the -1/2. But this subscale thing has a direction. So for example, the first term says that it's only take the nonlinear element case row and case column, which means that the effect of case column on the jth row is not there and so on. Okay. And this E2 has only the non-zero element right at the k location. Well, in any case, the Green function reveals something about the propagation of a primary wave, but also the secondary wave. Okay. And the equation itself is not hyperbolic, it's not parabolic uniformly. Therefore, certain hyperbolicity components there. So initial data is a delta function, and delta function propagate into the solution. No. Oh yeah. Well, how much time do I have? I have no time. 20 minutes. Yeah. Okay. Let me get Okay. Okay, yeah, I got it from Sensei. Oh, sorry. Okay, thank you. Okay. All right. So the Green function is, of course, is something one would like to know, but usually it is done by the functional analysis, and it's Yang Zhen in her dissertation. 1994, that she used the Fourier transform, and that is has been done for this Kawashima-Shizuda type equation by the Kyoto school. But usually you look at the decay in L2 norm, and that's very good with the Fourier transform, because Fourier transform is isometric in that. But Yanni just took the trouble of actually invert that Fourier transform pointwise. Okay, and she did that for P system, and later on generalized to the general system. So why bother to look at the green function in such a detail, the fine detail, the pointwise estimate, and so on? Well, that is because if you want to study something quantitatively, the first thing one should think of is the green function, and you want to know that rather pointwise sense. So let me mention one result that which is the shock wave. How does you have a shock wave? How does a wave propagate across that shock wave for the viscous conservation law? And here's one theorem. I don't want to show you this detail, but and then I give you more detail. It says that if you perturb a shock wave, which of course is the source of all the fun and the trouble in this business, if you have a shock wave and you make a perturbation, then the perturbation will propagate toward the shock. Some just stay into the shock because shock is compressive. That's what makes it dissipative. But some will be transmitted, some will be reflected. And all this coupling effect gives rise to something like this. It says that if you have a shock wave, I did not tell you what a shock wave is. The shock wave is you have a characteristic lambda p, and if they compress it, then you get a shock wave. And this shock wave, if I make the speed to be 0, and it connects to state u plus to u minus, then the shock wave itself will be compressive, which means that lambda p, the characteristic that compressed to form the shock, at u minus will have to be greater than 0, greater than lambda p, u plus. And this is called entropy condition. Now I'm talking about what if I make a perturbation of this wave, and how does it propagate? And the result is this theorem. The theorem says that there will be lambda I direction, and it's a decay like psi to the 3/2 and so on. I did not tell you what the psi is, and I will tell you very soon. And then there's a coupling called lambda I and so forth. You don't really want to know the detail of this thing, but let me say that I have a previous page taken away from the perturbation, the shift of the shock wave, some Berger wave. So this VI really is the higher order, the secondary part of the perturbation. And the secondary part of the perturbation decay in L1. The perturbation itself doesn't decay in L1 because it's a conservation law. But the secondary decay in L1 at the rate t to the minus 1/4. This is a surprise. If you look at the dissipative system, well, the simple one is the heat equation. If you take out the primary part, which is the heat kernel, you take out the heat kernel doesn't decay in L1. But if you take away the heat kernel, then it decays at the rate t to the minus 1/2. if you center the heat kernel so that the center of mass is right, you do one more thing, then decay T to the minus 1. Okay. And here is decay only T to the minus 1/4. This just simply indicates that for this system of viscous conservation law, the coupling is strong. Here is the Euler's coupling function, which is T to the minus 3/2 and so on. And the proof of that theorem, which occupied me several years and on and off over quite a long period of time. The latest thing is only finishing. Okay, so one is to approximate the Green function for the shock wave and use pointwise estimate to control the interaction. Okay, so this is reference, let me skip that. Now, the Boltzmann equation. Oh, I forgot what time did I say.
I give you the watch is 46.
46, okay. So let's see the chairman is consistent or not.
12 minutes.
What?
12 minutes.
12 minutes. Oh, thank you. Thank you. Okay. The Boltzmann equation now. Now, Boltzmann equation is dissipative because of the H theorem, which is a consequence of the molecular chaos assumption, saying that particles are basically uncorrelated before they interact. So here's the Boltzmann equation, which is transport part, collision part. And the collision part conserves energy, momentum, and mass. This page, I have shown it so many times, and I have gone through it so many times when I give a talk. But it's a difficult page, still difficult for me. Okay, so that's a conservation law, which is connected to viscous conservation law and hyperbolic conservation law somehow. And it's a conservation of mass, momentum, and energy. And this equation is not self-contented because the stress tensor is not a function of this mass, momentum, and energy density. You need to know F as a function of the microscopic velocity c in order to compute that. Okay. Nevertheless, there's an approximation of this conservation law, which will give rise to Navier-Stokes equation and Euler equation. So that's the H theorem, which says that if you multiply the function by log f, usually should be divided by C0. I should always keep that in mind. And then it's less than or equal 0. And it's 0 only f as a function of the microscopic velocity c is Gaussian. So this is the Maxwellian. And the collision operator is 0 when f is Maxwellian. So therefore, we will say that Maxwellian are the critical point of the Boltzmann equation. They are the only one constant solution of the Boltzmann equation. And if f is Maxwellian everywhere, which is hardly ever happen, but if it is so, then the stress tensor, which is the force you experience when you put your hand in the gas, if it's Maxwellian, then it's only force perpendicular to your hand, so it's only pressure force. And the heat flux is 0. And the conservation law become Euler equation. Okay. Now, the H theorem says that sorry, it's a kind of 30 page. H theorem says that the expression here is negative. This expression is negative. Well, this is because the log is an increasing function. And it's 0 only when f is Maxwellian. And so therefore, one can think of this term basically like this, minus the square of mf minus f square over k, which is not exactly true, but something like this is true. And you say that the solution, and this is theorem of Kahneman, you look at all the Maxwellian. Maxwellian are the constant solution of the Boltzmann equation. And look at all of them and collect them. The Maxwellian depends on density, fluid velocity, and the temperature. So it's a 5-dimensional manifold. So each point here represents a constant state solution of the Boltzmann equation. And Kahneman showed that if f is a function of t and c only, not a function of x, then the solution will just go right into its Maxwellian exponentially in time. Now, in general, though, the solution is space homogeneous. And then you not go into 5 dimensions. You go along different route, and then hang around here in this manifold. So this is a fluid-like kind of motion. And so the Boltzmann equation started in a very, very rough sense, consists of the understanding of this part and this part. And this part is particularly difficult to understand because it involves the nonlinearity of fluid motion. Now, this now leads us to this important open problem. Suppose one take k, the mean free path to go to 0. Well, you multiply this k to the other side. If k go to 0, this side go to 0. So q should go to 0. As q go to 0, we know that q is 0 only at Maxwellian. Therefore, one will think that f go to its Maxwellian. But if f is Maxwellian, then Boltzmann equation reduced to order equation. So the problem is to show that Boltzmann solution go to the solution of the order equation. But order equation has a shock wave, and therefore this process is very singular. In the sense that as k go to 0, you multiply k to the other side. K go to 0, this side may not go to 0 because f sub t greater than f may go to infinity. And therefore, whatever I said is true only almost everywhere. Meaning that it is not a strong solution of order equation, but a weak solution of order equation with shock wave. So this is a problem that I'd like to mention again. This is a difficult problem. The difficulty is manifold. One is that this process saying that you want to go to this manifold as k go to 0. But going to this manifold is complicated. You go in and then hang around it. And hanging around it is a never stop type of thing, which is, as we know, already is an open problem. And how to go to here? And there are a couple this picture is terribly simplistic. Okay. So in any case, this is a good problem. Okay. And you should, as I said, you should tell your student or the children of your student. Okay. All right. I want to advertise for Professor Sonner's 2 books, which is right on the table there. Is give you a very rich information of the fluid dynamic kinetic thing. So, God, I have this watch, which is very accurate, but I cannot remember what time I'm supposed. Well, do we still have time or not?
Yeah, it says take 1 or 2 more minutes and take 1 or 2 questions.
Okay, okay. All right. Now, I have talked about the study of a bottom equation. However, and there was a work by Sixian Yu on the Green's function, and all this do contribute to some understanding of the Boltzmann solution. But let me skip that. Instead, I raise another important open question. All right, so we are talking about dissipative system. But Boltzmann equation was derived from Newtonian particle system, Liouville equation, and that is not dissipative. That is reversible process. Now, the derivation of the Boltzmann equation from the interaction particle system is done under very special circumstances. The number of particles go to infinity. The particle becomes smaller and smaller. But this is wrong. It's nd squared. Sorry, that's a terrible mistake. Nd squared is fixed. Nd squared is fixed. If I fix instead of nd squared, say nd cubed, which means that the proportion of the room occupied by the particle is fixed. But this is rarefied limit. So instead of nd cubed fixed, it's nd squared. Here's a square, okay? So this is called Boltzmann graph limit. In that limit, this molecular K assumption assumed at the initial time will persist in the limit. Okay, not before the limit, because when wave interact, you lost that independence. So this is an open problem to show that the Boltzmann equation solution can be taken as a limit interaction particle system under the limit nd squared fixed, and under assumption the initial data has this independence condition. There's a paper by Stanford in '75. He did it for a very, very short time. So this is an important open problem, and it is a problem which can only be settled by analytical means. So it's philosophically important and historically important. Okay, thank you very much.